Inside a climate-controlled laboratory, this computer vision algorithm is a masterpiece. During validation, it achieved 98.7% accuracy, spotting targets on a pitch-black ocean in milliseconds. But as dawn breaks over the Pacific, the physical world does something the model's designers did not prepare it for. The sun warms the ocean surface, creating thermal currents and solar glare. On the operator's screens, the algorithm begins confidently targeting cresting waves. There are no software crashes, no syntax errors, and no broken lines of code. The system is running perfectly. It is just completely, silently wrong. This is the Sandbox Illusion. We build artificial intelligence inside designed landscapes, sterile, curated simulations made of historical data. In these pristine digital rooms, our models are flawless. But developers frequently mistake the map for the territory. The moment an AI crosses the boundary into the wild, it leaves the simulation and enters an unmediated, chaotic reality. It is a world that does not care about our training sets, and it is a world that refuses to stand still. Under the hood of modern neural networks lies a highly fragile mathematical assumption, stationarity. It is the belief that the statistical properties of the future will always mirror the statistical properties of the past. It is a convenient lie. In the real world, human behavior, weather, and markets are non-stationary. They drift. When reality shifts, the elegant mathematical boundary the model drew during its training phase remains frozen in time. The world moves on, but the algorithm is stuck in the year it was born. This divergence manifests in distinct ways. The first is covariate shift. Here, the underlying relationship between inputs and outputs remains the same, but the distribution of the incoming data changes. Consider our thermal drone camera. A ship is still a ship, and water is still water. But because the midday sun has warmed the sea surface, the range of temperature inputs has shifted completely out of the spectrum the model was trained on. The math is still sound, but the model is blind to a reality it has never seen before. Then, there is a far more insidious mutation, concept drift. This is not just a change in the data coming in. It is a fundamental rewrite of the rules of the game. In late 2021, this exact shift triggered the sudden collapse of Zillow's automated home buying division. Their algorithms were trained on decades of housing patterns to predict future value. But post-pandemic economic shifts severed the relationship between past prices and future demand. The inputs, like zip codes and square footage, looked normal, but their underlying meaning had decayed. The model kept purchasing homes at prices the human market would no longer support, resulting in a $500 million write-down and the termination of an entire business unit. The most dangerous attribute of algorithmic decay is that it is completely silent. When traditional software breaks, it crashes, throws an error code, or drops a connection. But when an AI model drifts, it fails confidently. In a rural health clinic, a diagnostic algorithm trained on high-resolution clinical scans might be deployed to handheld, low-cost cameras. The software will not crash. It will process the noisy, low-quality image and confidently output a clean bill of health to a patient with active diabetic retinal bleeding. The engineering dashboard shows 100% uptime, while a human being is quietly losing their sight. To survive this landscape, we must stop treating data as a static reservoir and start treating it as a high-velocity river. This is driving a fundamental shift in computer science away from offline batch training toward real-time data stream mining. Researchers have shown that in a non-stationary world, static models are obsolete the moment they are compiled. Organizations are realizing that deploying an AI is not a one-time product launch. It is an exhausting, continuous infrastructure challenge, requiring real-time feedback loops, automated retraining, and constant monitoring just to keep the algorithm from drowning in the stream. We like to imagine artificial intelligence as a collection of steel-clad, permanent machines. But the mathematics reveals a far more fragile truth. An AI model is not a monument, it is a digital garden. The very second we stop weeding it, pruning it, and feeding it new observations, the wild environment begins to reclaim it. We cannot build a perfect mind, launch it, and walk away. We can only build fragile mirrors of our past and spend every single day working to keep them aligned with an ever-changing present.